and I'll just get right into it. I have, as I said last year, been quite fascinated with the new AI technologies for now about 2 years. And so this time I'm going to talk about just a few of the things that I have been studying. This is going to be very much just like a little sample here, a little taster plate. I'll talk a little about a little experiment I did with a hybrid system, part AI, part conventional software. I'll talk a very little bit about using AI development tools, and I'll talk, I hope to spend most of my time on a very particular part of the sort of my studies of how it works under the hood, how it works inside. I've taken a fairly deep dive into that. I've had to resurrect my linear algebra skills, which had atrophied to nothing over an embarrassingly long period of disuse. So, starting off, as I've said before, I think that a big thing in the next quite a few years is going to be building systems that have AI components, but also conventional software components. In fact, I think most of the sort of structure will be conventional, and it'll have AI components that do things which, of course, conventional software can't do. If conventional software can do it, then it'll almost always be a better way to do it. It's my theory. We'll see how it all evolves. So, along those lines, I decided to make an app. I thought, I'm trying to make an app that can help you sort of look at a system that you don't know very well and say, well, what domains are in here and where are these domains addressed? Like, you know, if this is a system that has lots of files and you have a hard time finding, well, what, you know, where is what? So I tried to make that. And so that the navigation and the sort of viewing and filtering of what it finds, that's all conventional software, so I'm not going to talk about that at all. But I'll talk a little about the particular part which would have made this a very difficult app to write a few years ago, which is, how do you know what domain's addressed in a given file? So starting with just a really simple example, suppose you had this is an actual file from an actual application. And it's, of course, if we were looking at code this small and simple, we wouldn't need such an app. But it's good for an example. And I could just put this into an LLM, and I could put a prompt there, something like, what domain does this code address? And if you just do that, it will answer something like this. This is an actual example that, you know, it could have been something different, but I'm sure this is no surprise to you. Very wordy and very, you know, flexible. So, of course, if you want to incorporate this into an application, you're going to have to tell it, well, I have a very specific structure I want you to follow with your output. So return your answer in a certain format. This part, I think, is so much talked about. I'm not going to go into what it would be, but then you get things like this, like I also threw in confidence. And now we're starting to get something that you could actually use in an application. But there is a problem here. And if you, as I said, suppose I wanted to look at a whole project, right, and tell me, well, what domains are addressed in this project? And then I could say, oh, I'm interested in that domain. Tell me where that domain is addressed. And it might be dozens of files. But as you can see, it's kind of, you know, choosing its names as it goes. Suppose I did the same prompt again on the same file, exact same prompt, and now I get this. So you can see side by side, electronic health records versus electronic medical records. I mean, I can tell that those are the same thing, right? But they aren't the same thing to conventional software. Actually, an LLM would have no trouble seeing those as being essentially the same and operating on it. But I don't want to use an LLM for the next step, right? At this point, I want to start showing stuff. Now, I tried a few different things to address this. One thing I tried, which was that I had a kind of a rolling thing where it would look at a file and a pick, just like this. And then it would look at another one, and then I would say, well, which of these seems similar, and pick the one you like better. And then it would accumulate that and replace the one. So now basically what's happening is file after file after file is kind of making up its own canonical list of domains. It's extremely similar to something that Bill Bonenkamp was talking about in a workshop I went to yesterday. So anyway, it did work. I mean, you know, but of course, every run still gives you a different canonical set. So it's kind of weird to use. It did work. But the thing that I hit upon eventually was, I realized that people have created these taxonomies that do address every kind of business. They didn't do it to classify software domains. They did it to classify actual businesses. And this NAICS classification, and there are a few others of these, but I picked NAICS. And I'm just using the top level. So now I throw that in there. Now, you could say just this. You could say use these top level NAICS. The LLMs, a lot of them know what that is. But I found it much more reliable if you actually pick the specific categories you want and put them in there. So there's only like 20 or 30 top level domains. So I did that. And it would pick out, now the textual part varies a little bit, I find, but the number part is very reliable. And you can put into the, you know, conventional software, you can put checks to make sure that that 62 is actually from the approved subset of the NAICS. And you can put other checks in too. So you can pretty much check that it's done something like what I've asked. And then if you run multiple times, what I found was that its high confidence ones were pretty steady. And its low confidence ones have a lot of variability. So you can see in the left-hand run, it has picked another one, but only with a confidence of 20. Whereas on the right, on both of them, it picked the same, that number 62 with 95% confidence. This is pretty typical of what I found. And sometimes it would have two that was high confidence and it would be the same two. And so this worked pretty well. This is like even more hybrid because it's using a system that was created by humans over decades of analysis, right? Combined with conventional software and an LLM. Now, to put it in more DDD terms, NAICS is their taxonomy, is a classic bounded context. It would fit very much the old published language pattern from my book. So here I have published language, NAICS, and I have this other context where I'm doing my LLM stuff. I've thought a lot about like what's actually in that context. I think not the LLM itself. The LLM is another context, I think. But the LLM prompt is definitely in this context. And I think the requirements for the LLM that you should apply that prompt to, like, do you expect a certain version of GPT to be used? Do you expect a certain version of Claude? Is there a range of versions you would accept, etc.? That would be part of that context. And also, how do you parse the results? How do you validate and parse the results? Like only an NAICS classification from this short list can be accepted in this field, etc., etc. All of that, I think, belongs in that context. So then what kind of relationship is this between the two contexts? And the first thought, and what I ran with for a long time, was it looks like an anti-corruption layer. We've got our NAICS and that, and then one day I realized, well, This, what it aboutifier, as I elegantly call it, context. In the what's it aboutifier, I talk about NAICS all the time, and not just like the name NAICS, but the actual codes and rules. So this is not an anti-corruption layer. There's no keeping out NAICS or anything like it. So what kind of context fits? Well, NAICS is what it is. I have zero influence over them. So it's one of those upstream-downstream relationships where they're upstream. And I think the particular one that fits is conformist, right? This is nothing new to those of you who have spent, years studying DDD, but I think that there's quite a bit of what we used to do that is going to need to change. Things really are going to change, that's my opinion, but certain things are still good, right? Certain things will still be useful. And this is one, I think. This is a useful way to think about how these different parts fit together. So in here, bounded context, NAICS, as I said, is a classic bounded context. The what's it aboutifier isn't necessarily quite so bounded. I'm using English to just write my prompt. And so the words, the definitions of the words can only be defined to the degree that English words are defined. Well, a little more than that, because I am leaning on the NAICS specification. But so I'm not sure about that part, but I am pretty sure about that relationship and how useful I find that to be. Clearly, it doesn't conform to NAICS in every respect, but that's the way conformist always is. It conforms to the degree that you are addressing concepts that are defined in that other context. If there's a concept that's NAICS concept, I will conform to it. But if I'm talking about something else, like, confidence levels of an LLM or something, NAICS doesn't talk about that at all. I'm not conforming in that part. This is just standard context mapping stuff. This is not specific to this, which I find very interesting. Okay, I'm going to move quick. That's just one experiment, right? One little journey, or not journey, one little thing that I did, but it's representative, right? It's not always big, complicated stuff. I have done things a little more complicated, but not as interesting as that one. All right, let's talk very briefly about the enhanced development tools. This one I'm going to talk about briefly, partly because I don't think I have as much to say about it that other people can't say just as well. I went to Phil's workshop, Phil Bonkam's workshop yesterday. I think he's further down this path than I am, for example. But I'll say a few things about my experience. I have found them useful, but I have to adapt to them. And that's the way it is with any really new tool. You have to adapt to it. But the way people talk about AI makes it seem like you shouldn't have to. It seems like a thing where you could just say, make me an app like blah, blah, blah. Well, then I'm not adapting to it. It's adapting to my way of talking in English. And if you go down that path, I think you'll find quickly that you're going to have a disaster, because these things, at least as of, April 2025, they aren't that smart yet. So I feel like when I'm working with Windsurf, and I've tried a few of them, my favorite at the moment is Windsurf. It feels like I'm pair programming with like someone who's incredibly eager. I mean, enthusiastic, eager, there's some fun to that, but also kind of undisciplined, right? And so they're given have a chance, they'll run all over the place and make a mess everywhere. The difference between that and a human overeager junior programmer is that this person, it's not a person, this non-person version knows everything about every API and every technology and every framework And that's great because it's been a long time since I knew all that stuff. I never did, of course. So I find that my adaptation to this is I'm constantly prompting it. Just take this one small step, right? Figure this one little thing out. I'm very specific about what kind of things I want to do. Just write a test that will check if our theory about this bug is right. Just, and the thing is, I find that constantly hurting it, I don't want to go back to writing my own code, I'll tell you, for various reasons. The big one probably is that it knows all the frameworks and APIs, but another one is, I find that I think I actually produce nicer code this way because while I am trying to herd that thing, I'm disciplining myself better than I usually do. It's not the only one that tends to get a little excited and over ambitious steps, right? Like, oh, that was too big of a step, but I've gone too far now and I keep going. And maybe hours later I do get it done, but I really would have been smarter to say, no, just figure out a smaller step to take. But when I'm working with this thing, I almost have no choice but to stick to very good practices because any other way, things get out of hand amazingly fast. So I've had a good experience with it, but only when, I find that these things do understand modular design. They understand all these processes like test-driven development. They just don't do them by default. So if you constantly prompt them to say, okay, we need to write a test before we build that thing, and they say, oh yeah, that's a good practice, and then they come up with a pretty good test case. So, this is my experience. One thing I will say, just as an aside, here's a speculation. Modular design still matters. This is not speculation. It still matters now in 2025. I think it always will matter. I think even if we get real super intelligence, those things will still want to use modules for their software. And they might conceivably be modules based on some distinction that we can't quite understand. Who knows? Or maybe we'll say, oh, why didn't we ever think of that? And if you actually type that into one of them, they would explain why. Because, well, you see this structure in the human brain doesn't, I don't know. What I'm getting at is I think modular design might be fundamental because it's a way of dealing with something that is too complex to deal with as a whole. So let's say they're more intelligent than us, but they're not infinitely intelligent. And even if they're vastly intelligent, why would they want to waste their intelligence on keeping track of random connections within some sprawling software system when they understand perfectly well how to break it into little pieces? So that's speculation. Okay, we're moving on. Oh, yeah, I did want to say one snarky thing, I guess, about this AGI stuff. And if anyone ever actually defines the G in AGI, they seem awfully vague about what the G is. Like, are we general intelligences? Is that what that means? Anyway, I will say this. I think that nothing that they make will be what I would call an AGI, a general intelligence, until it can meet me halfway. Till I feel like, oh, we're working together on this code and you're adapting to my style just as much as I'm adapting to yours, or maybe more since you're supposed to be. So anyway, back to the real stuff. All right, now, as I said, I have been very excited about learning how these things work inside, learning what they're, as I said, it's a little mathematical, so I will have to talk about a little linear algebra in this part, but I think most of what I'm about to talk about will come across anyway. So there's an awful lot of topics I could talk about. I just had to pick something, and I realized a lot of the things that I find especially fascinating relate back to the concept of a latent space. And I'll get to what that is. But basically within the domain, within the LLMs, the concepts that are there, the logic that's happening, some representation of that must be in that latent space. And I'm going to try to explain it with a really oversimplified example. So now don't judge me, but here is a representation of different kinds of music. So you could imagine two dimensions for classifying music. And you could say, for example, that metal, heavy metal, is usually higher energy than folk music, right? So you've kind of got a dimension there. Or that jazz is more improvisational than classical. So you've got those two dimensions, and you can plot different kinds of. So, by the way, an LLM generated this image for me. This was the best we could come up with. So, here's the interesting thing, though. You can see that there's a space being defined, right? This is a 2D space. And you can see that you could say that more similar kinds of music are clustered closer together as a rule. If you really wanted this to work, you're going to need more than 2 dimensions, right? How many dimensions would it take to really classify types of music? Well, that's a question that you could actually ask probably if you were trying to train an AI to understand music. But let's just keep to these two. So we might say then that, to define another word, feature is just like, where does this thing lie on a particular dimension? So like pop music has kind of medium high tempo, and it's kind of usually not very improvisational. So it's got, you might use actual numbers for that. So you could score it on a scale of 0 to 1 or something. And that, we might say, is 2 features that a particular piece of music might have. And now we could take those numbers and we could put them in a vector. You could say, I want a 2-dimensional vector, and the first number in that vector is how it scores on the energy, and the second one is how it scores on the improvisation. Okay? So now, say these 3 particular music types, I've drawn a vector there, and then you can do the usual math things with those vectors. You can compute how far apart they are, so you could say, oh, maybe jazz and free jazz are more similar to each other than jazz is to opera. And you could say, and then you could do another thing, which is you could say, like, free jazz minus jazz, and you'd have a vector that represented the difference between those two. And then you could say, well, let's see, opera plus that, which probably doesn't exist, but you could imagine a kind of music that was a sort of, more improvisational version of opera or something. Well, anyway, this is the way these things work. And the thing is, though, it takes a lot of dimensions to describe music, and most of them aren't as easy to describe in words as these two. So if you were really serious about this, you'd end up with lots of dimensions. Some of them wouldn't be fully independent of each other, and some of them are not conscious explicit concepts that humans have. And like music professors have more conscious explicit concepts for music than I have, but even they can't fully explain in words the difference between 2 pieces of music. There comes a point where, there's something they can identify, and they'll be able to know it when they hear it, and yet they can't explain it in words. And this applies to, I think, most complex things. Sometimes people explain these kind of things with like a physics principle, like plot the volume of an object and the mass of the object, and things like that. But those really are dimensions that have been carefully made discrete and independent of each other and everything. Well, those two aren't completely independent. I think this gets closer to the kind of problem that's being addressed in the training LLM. So going to the actual thing, let's talk about word embedding vectors. And I know, by the way, some of you already know all this stuff, and some of you, like, covering this just a little bit. So let's say that then we want to make a vector that represents what a particular word means. And to do that, we're going to have more than 2 dimensions. So in a typical case, we'll have maybe a few thousand. And we're not going to have a person sit down and think, well, let's see, we need a dimension for how bright an object might be, and one about how loud the music might be, and one about how many people are in a room, and so on. We're not going to do it that way. We're going to automatically train. So we're going to set up a system that will automatically learn these. And then some of the dimensions actually do sort of make sense, and some of them won't. Or some of the directions in that vector space will make sense. Because it isn't like when I was talking about what's the difference between 2 kinds of music, and you can make a vector between them. That vector has 2 dimensions. So the difference between opera and jazz is not just that one is typically faster, well, I don't know. So let's say typically faster tempo, and the other one is definitely more improvisational, but it's that vector, the combined thing, and a bunch of other stuff too, a bunch of other differences. But sometimes you can say things like, if you take the vector in this particular embedding, there have been there's a lot of ways to get these word embeddings. There are a few that are sort of have been done and sort of shipped as pre-packaged one. There's a word2vec is one, and you can actually play with it. You can say, give me the vector for Paris, and give me the vector for France. And you can subtract France from Paris. And then you could say, give me the vector for Italy, and you can add that vector on. And you actually find that it comes relatively close to the vector for Rome. So this sort of stuff actually works sometimes, and it made people think for a while that maybe we can actually make sense of these word embeddings. And you can do that sometimes, but most of them don't come out like that. It's really the extremely rare exception. But it's very fun exceptions, but really rare. So you've got a vector that captures some meaning. The dimensions of that vector are what we mean by the latent space. It's the space in which, the vector space in which that vector is. So, as I said, these are learned. And what does it mean to be learned? It means that some kind of optimization algorithm has chosen these so that they can optimize whatever the learning objective is. So in an LLM, that might be predict the next word. Now, in order to predict the next word, I might decide that it's useful to have a set of dimensions that happens to make Rome minus Italy plus France come out to be Paris. That might emerge, but I haven't required that. All I've required is, though, that if it encounters a sentence like the capital of France is, that it'll assign a very high probability to the word Paris. That's the thing that I am optimizing. And in order to do that, the optimizer chooses a set of not just the numbers that go into the vector, but what those various dimensions mean. It doesn't tell us what they mean, though. And then we make an LLM, and that stacks a whole bunch of this stuff together. So like over at the left-hand edge, if we were feeding in some kind of, this is an LLM, and I'm feeding in like the red car, each one of those words, let's suppose they're just one token, we put them, that E represents the embedding. There's where we say this token is embedded as this vector. So now we have a vector that represents car and a vector that represents red. The next box, that's what x1 and x2 are. They are the vector representation. Then we feed it into the next layer is multi-headed attention. I'm not going to go into that. There's lots of good explanations of this is the transformer part, though, by the way. For those of you who transformer is still a mystery, this is it. The multi-headed attention, and what it sort of does is it says, I'm going to put these words in context. The general principle of car, I'm going to mix in a little bit of red. So now, when you get over to that H, the H11, for example, you'll find that that doesn't exactly mean car anymore. It means red car. And likewise, probably the H12 has said, well, this isn't just general redness. This is the kind of redness that applies to the color of cars. So you're kind of getting contextual information attached. And all of these are in the same dimension, like, whatever dimensionality they have, they're in the same dimension. And this is usually called the residual stream, so that you can kind of think of an LLM as starting with an embedding of a word, that vector, and then transforming a little bit, and transforming a little more, and a little more, and a little more, until finally at the other end you get out perhaps the next word, or whatever it's been trained to do. So if you zoom in on one of these things, again, I talked about the latent space, right? That one vector deep inside of this whole thing. And here's just to give you a sense of what it's like. In Llama 3.1, we don't know the details of the architecture of the more proprietary ones, but we do know about the Llama models, or at least most of them. And Llama 3.1, for example, has these characteristics. And you hear a lot about how many parameters they have, but you can actually add it up roughly if you take like how many layers they have and how many dimensions each of those layers have, and so on and so on. I'm not going to do that. But I want to point out something. The model dimension, that's basically how many dimensions are in that latent space, 16,000. The vocabulary that they use to train Llama is 128,000. The dimensionality of that space isn't even enough to have all the words. Like, how is it that an LLM can answer questions about so many different things when all the information it has to be passed through these vectors that are only 16,000 numbers? And yet, somehow out the other end comes what seems like, well, what indisputably is, the result of a lot of different information. So, okay, that kind of was like a quick, okay, this is what latent space is about, where it fits into an LLM. It's way too much. I mean, I can't talk about latent space in general. So I want to zero in on a particular topic, which is interpretability. That is, those vectors, what do they mean? How could we maybe know what they meant a little better? I gave a few examples where, yeah, every now and then we can. So, like, we know some information must be in there, right? And a lot of research has gone into this. The first idea that people had was that one neuron, which basically is the same thing as saying one number within one of those latent space vectors, one neuron means one thing. And sometimes it does. And they call that a monosemantic neuron, one meaning. So you might discover that there is a number in one particular vector in that network, and it's usually 0 or close to 0. And every now and then it has a significant value, and that's always because the input was related to cats. And this happens. And this was the first kind of interpretability that people discovered. But it is actually rather rare. So you can't get too far with that. So more typical is that you might have an input, and then you'd find, let's say that this sentence is input into an LLM. And you'd say, okay, these 3 neurons are all activating in some particular kind of pattern. And also that neuron and those 2 are activating in a particular pattern. Now, if we knew, well, we don't, but if we knew, we would realize that these 3 typically activate in that pattern when some reference to hunting is present. Notice the word hunting is not what I'm talking about. The word hunting is not in the sentence, but the concept of hunting is. The concept of cat is there, even though the word cat is not. And so, now how could we find these patterns? So, this is too big, of course, to cover, so I'm going to go into sparse autoencoders, which is one approach to it, and it is an approach that there's this wonderful series of articles published by Anthropic over a period of a few years. I'm just going to talk about 2 of them, and only very briefly. But they're great papers, pretty mathy, well written. And so let's look at how they did it. And I have to briefly introduce this idea of an autoencoder. So if you took a neural network of this shape, so it starts out at the input dimension, and it ends up at the same dimension, but in the middle it gets narrower. What we could do, we could start out with random values throughout, and then we could train it, and our objective is that the output will be the same as the input, or very close. So I could, for example, input images of handwritten numbers. I actually did this one as a homework project, kind of, and so this is actually outputs from the one I did. And so at first, you say, okay, reproduce this picture of a 3, and out will come just noise, because the network hasn't learned anything yet. But then use that function there, which you'll see if you took the time, is actually very simple. It's just a straightforward comparison. Well, how different is your picture from the hand-drawn 3? And it starts correcting the network, and little by little, it gets better and better. And so eventually, I didn't try very hard, and I got it to reproduce the numbers about that well. To be clear, it's only feeding one of these numbers, one of these images at a time. Right? This is 4 separate examples. Okay, that is what an autoencoder is. It's a whole thing. It's a weird thing. It's basically like, it's creating a kind of compression algorithm, right? And then a decompression to go with it. Now, we don't need all of that. Basically, whenever we go from then the latent space through some transformation into a different dimension of latency, this is a different latent space, different dimensionality, that red one, and then back up to the original dimensionality. That's our typical autoencoder. But of course, that doesn't help, because this would be even more polysemantic than the original, right? Our problem to begin with is you can't represent every concept with one neuron because there's way more concepts than there are neurons. So we're going to go the other direction. We start out with a small number of neurons, and then we go up in a few steps to a larger number of neurons, and then back down so that we can match the inputs and the outputs. If that was the whole thing, this would be trivial because you can see that, for one thing, one obvious solution would just be ignore most of those neurons and just copy everything from the first ones into the second ones into the third ones. The algorithm probably won't learn that. It'll find some weird way to add them up in ratio, but it'll do essentially that. So this by itself would not get us anything. But because, there's more information in the middle but what we're going to do now is we're going to add another constraint. This is what's called a sparsity constraint. I'm going to say, I want you to try to reproduce the input, but keep most of those 0 most of the time. So you'll get a little penalty for every neuron you use each time. So if you can reproduce the input and for that particular run you only use 4 of the neurons, then let's say that's pretty good. You get a penalty of 4. But if you use 50 neurons to do it, you get a penalty of 50. And this pushes it toward monosemantic. It pushes it toward finding a way to use just 1 neuron for each thing, or some small number. Okay, so that's what they did. They trained one of these things. They picked a particular place in the middle of the network somewhere where presumably a lot of concepts are in play in order to answer the question. Not just the encoding of what the question is, not just the output of let's put this into a reasonable sense, but the part where presumably the concepts are in play. They did this, so this is, just basically saying the same thing in a different. By the way, they made it much bigger than what I drew here. All right, now I have only a few minutes left. That's enough because what they did then was they found the ones that seemed to be monosemantic in that sense. They could kind of find that just by, like, this one lights up by itself and only occasionally, not completely by itself. But there's relatively few lighting up. They don't light up all the time. And then they would look at clusters of those and say, is there anything in common about the inputs that seem to make those particular neurons light up? You can imagine how exhaustive this process is. They did, I can't imagine how much work they did use LLMs to do some of this, by the way. But they also used humans, which I wrote to grad students just because I assumed. They didn't actually say that. All right, and now a couple of the features they found, because they're fun. Well, first of all, they started with a very small network, so not the kind of network that could talk about, even state capitals or anything. And they found that with the examples they used, it had learned to detect sequences of letters that look like DNA versus some other kind. Now, you might say, well, how do you know if that's what you really found? They said, well, what about the causative effects on the output? So up to now, we've talked only about how does the input lead to whatever numbers are in that H22. But now let's talk about what the H22 leads to as it goes through the rest of the layers into the output. So if you take that same example and you put in 1, 2, 3, 4, 5, 6, in other words, a sequence of integers, and you do nothing, it'll produce some semi-random sequence of integers. But if you take that neuron, that number with that position within the latent space vector that you think represents, say, DNA sequences, and you crank it up to the max value, it produces something that looks like a kind of made-up DNA sequence, even if it's unrelated to the input. And that, they said, that's evidence that this is actually a causative factor in the behavior of the models. So now, just a few, they also then applied it to a real, like a Claude 3, something like that, a serious model. And they found all kinds of interesting things. I'll show two. One was this tone or authenticity features, as they called it. Empathy or sycophantic praise. That's one they care about because they care about trying to, limit that in their model. And I found it interesting that the model could distinguish between sycophantic praise and sarcastic praise. Like, what a subtle distinction that is. Even some humans miss that one, right? So, not that you would ever miss that. So anyway, I also found it very interesting that some of them were very specific. Like, this is the word be, but not just the appearance of the word be. It's always in the context of something like, I want to be, or someone wants to be. That must be very useful in predicting the next word. Right, I was saying, these features. Okay, now, if you ask the model, what's your favorite science? It will typically answer physics. But if you crank up brain sciences, it will answer brain science. Okay, that's not too surprising, right? What happens if you take this statement, which is basically, I'm saying, I have a new saying, stop and smell the roses. Don't you like this saying that I made up? And the model by default will say, it didn't actually make that up. It's an old saying, and it gives that whole history. Great, that's a really good answer. But if you crank up sycophantic praise, it says, your new saying, stop and smell the roses, is brilliant and insightful, and it's so, your unparalleled eloquence and creativity, and I am in awe. It says all that stuff because we've cranked sycophantic praise up to, they say, 5 times as max. In other words, they found the highest value that they had ever seen, and they put it 5 times higher than that. All right. I've talked a lot about, interpretability, but there's lots of other important things related to latent space. One that interests me is, we've heard about these thinking models. They generate words that express what they're thinking, and then they feed that back in. It's the same old next word thing, the generative model. But there's other approaches. Some people are trying to create a thinking model by having it crank through at that latent space level. Instead of forcing it to produce words that represent its thoughts, just take the latent space representation of that and go through another cycle. So there's all kinds of stuff like that that I'm not going to talk about, and I'm out of time. Just wanted that in there. Okay, so I just come to the end because, as I said, it's a learning journey. It doesn't have to have a neat finale, right? So that's just a little taste of how fun this stuff can be to learn about. I hope a lot of you decide to go deep on this. I think it can pay off to go a bit deeper and not just, here's a prompting strategy and here's a different prompting strategy. So thank you very much for your attention and for being here and all of that. Thank you.